We continue now with the kinetic modeling topics, moving on to reference tissue-based modeling, in other words, avoiding blood data. Reference tissue kinetic models were developed to avoid the complexities of collecting blood data for classical compartmental models. However, there are critical assumptions that must be carefully considered. The reference tissue must be completely devoid of the tracer target, yet have very similar tracer delivery and washout to the target region. In practice, we assume that the ratio between K1 and K2 will be the same between the target tissue and the reference tissue. Violation of these assumptions can lead to bias in the model results. Assuming we do have good agreement between the ratio of K1 and K2 between the target tissue and the reference tissue time activity curve then provides the information about tracer delivery to the target tissue that would otherwise be provided by the blood data. This means that the two-tissue compartment model could be simplified. It's important to note that in small animal PET, even when a reference tissue is available, it could be compromised by spill-in of activity from adjacent regions that express the target or have high non-specific uptake. In this example, we will use data from a rat imaged with 11C raclopride, a tracer targeting dopamine D2 and D3 receptors, which are densely populated in the striatum in rodents. The cerebellum is then routinely used as a reference region for non-specific binding. We will use volumes of interest from an atlas-based workflow to extract the striatum and cerebellum time activity curves, and then go on to perform the reference tissue-based kinetic modeling. Once again, we start kinetic modeling with time activity curves, so we extract them from the PET data. We'll do this using the View tool, and we'll use data from the Bruker PCI database, selecting rat7 external, which is this rat brain raclopride study. From the series, we should select the dynamic PET matched to the anatomical MRI that has been cropped to speed up the processing. Once the image is loaded, we can use the time frame slider to explore the data, noticing that generally in the earlier frames the image is rather noisy. In the later frames we see more of what we expect, which would be high tracer uptake in the striatum with almost no specific uptake elsewhere in the brain. An average image can improve the image quality and reveal the specific binding, also allowing us to check the volumes of interest. Using the Tools tab, Average subtab, we can create an average of frames 30 to 39 without replacing the dynamic data. Then we can turn on the MIP display, which reveals the high uptake in the striatum, a faint outline of the brain, and high uptake in the Harderian glands. For this example data, we have provided the atlas-based VOIs in the database. So we can proceed to the VOIs page, where we can load the VOIs from the database. In this case, for rat7 external, you see several saved sets of volumes of interest. For the cropped data that we have loaded, we have the general atlas regions and then individual right striatum and cerebellum that you can use for parametric mapping in a later exercise. For now, select the atlas regions in the MR space and retrieve. These atlas regions were created by matching the T2 TSE 3D MRI in the database to the PX rat Schiffer template, and then the striatum and cerebellum VOIs were transformed into the individual MR space. The PET, in this case, has also been matched and resliced into the individual MR space meaning that the volumes of interest correspond. We can explore the regions that have anatomical shape based on the MRI, and naturally this may be limited compared to the PET resolution, meaning that we have this blob of PET uptake that doesn't necessarily correspond exactly to the anatomical shape. This is one of the compromises we make with atlas regions. The regions can be used reproducibly across many animals, but at the individual level we know that there can be problems like this. For now, we can switch to the dynamic PET using the list of images in the top right. Then we can calculate the time activity curves for kinetic modeling. In this case, we see two very similar curves for the right and left striatum, and we see a much more rapid washout of the tracer in the cerebellum. As model selection on the right-hand side, we can already select reference tissue models. And then, because we have the kinetic modeling tool open from the last exercise, we can use send add to create a new workspace. Now in the kinetic modeling tool, we see a tab for our previous exercise and the new tab for RAT7 external. Because the reference tissue model selection was made with the time activity curves, the radio button for reference tissue models has already been selected on the right lateral taskbar. Confirm that simplified reference tissue, SRTM, is selected in the model list. And note that you can call up help for the model using the question mark to the right. On the tissue tab, for the region of interest, we should select striatum R, the right striatum, and the cerebellum as reference region, as already configured here. Now we can click Fit Current Region to apply the model. We see that the model curve matches the data to a reasonable degree, and then we can read out our binding potential on the right-hand side. Next, we can change the target region to the left striatum and fit the model there as well, also obtaining our binding potential. The results for both regions can then be viewed in parallel using View Parameters under Tools in the lower right, where we can already note the difference between the binding potential in the right and the left striatum. Finally, from the kinetic menu, we can save the KM file using a similar name to the previously saved project, Simplified Reference Tissue Model, for our example, and then the project can be retrieved at any time.